Okay, so to start off today, we're going to start with a review of last time. So go ahead and get RStudio fired up with a new script. What I want you to do is to integrate some of the things we talked about last time. Namely, I want you to make a vector containing the numbers from 83 to 111. Then make a, sorry, that would be a variable. So a variable, which will hold a vector, but make a variable that contains those numbers. Then make a new variable that has the mean of the square roots of items 10 through 18 of the above vector. So you'll end up with two variables here. And the second one has the mean of the square roots of items 10 through 18. And so this will take a few different steps. It's meant to hit a lot of what we did last time. And when you have done this, please put the value of the second vector in the chat, which is how I'll know when people are done. All right, let's go. All right, and then just as a reminder, you have the functions mean and square root that you can take advantage of. All right, got the first people getting their answers back now. All right, we'll go about 1 more minute, and then we'll go ahead and call it. Okay, we're going to go ahead and call it for the sake of time. If you were not able to finish, I recommend come back and try this on your own in the future. We are going to go over the answer right now. So if you got stuck, hopefully this will help you determine what it was. So the first step here is making a variable containing numbers 83 through 111. So we'll just call this variable is 83 colon 111. You remember the colon operator gives you all the values from the start to the finish. And so if I look here in my console at what variable is, it would help if I actually ran the code first, wouldn't it? I have the numbers 83 through 111. Now I'm going to do this in 2 different ways. The first way is to sort of break it out into each individual step that most people do when they start out. And then as you get familiar with R, you'll be able to start combining things into more complex stuff. So we're going to start with the simple one, which is doing each of these steps separately. So I'm going to make another variable called temp1 so we have these 3 things we need to do. We need to take the mean of the square roots of items 10 through 18. So you actually want to start from this part, the last one. So let's take numbers 10 through 18. So remember, we can use this inside the square brackets to extract part of the numbers in this variable. If I run this, temp1 is the 10th through 18th values, so 92 through 100. So now I'm going to take, we just got these, now we're going to take the square roots. So I'm going to call it roots equals the square root of temp1. Again, looking at that variable, we get those square roots, and then my mean, I'm going to call the variable is the mean of roots. If I run that, my mean is 9.797073. So that is the mean of the square roots of items 10 through 18 of the numbers 83 through 111. So that's complicated. We stack 3 or 4 different things on top of each other in order to get to our final value. The reason why I made an exercise like this is because that's what most real problems are like. You know what you want to get in the end, and you have to unpack it to the 3 or 5, or in some cases 10 or 20 or 50 steps you have to do to finally get there. And so being able to think between this is what I want and this is what I have to do to get there is a very important skill. Now, as I said, as you get more comfortable with R, you'll get more comfortable with stacking some of these things on each other. So here I separated out the second part into 3 different steps. That could be done as a single step. We say my mean is equal to the mean of the square root of items 10 through 18 of variable. Actually, I'm going to call this one my mean 2 so we can keep those separate. So here I've combined all these above, the mean of the square root of our variable, which looking specifically at items 10 through 18. So if I run this, we look at my mean 2, we get the exact same answer. As far as R is concerned, we've done essentially the same thing. We just haven't saved all these intermediate variables. We just went straight to the end. There's a balance here. By doing this, you have fewer lines of code, and it's a little bit cleaner. It is, however, harder to understand exactly what's going on if you have to start picking code apart, because you can imagine if you try to nest 4 or 5 or 6 of these function calls together, it can get very complicated very fast, and so I don't recommend it. You'll have to find your own level of where you're comfortable with. And if what you're comfortable with is just one at a time, that's fine. Most important thing is that your code is clear and it's understandable. And that's actually easiest when you do things one at a time. So, any questions with this review part? Okay. All right, so now we're going to go on to today. Today we're going to talk about reading and writing data and data types. So this is the first part where we're going to be doing some things that are practically relevant to what you're going to be doing. Because generally speaking, reading and writing data is one of the most important things when you're doing analysis. And to start, we're actually not going to use R. We're going to zip over to Excel. I assume most of you, actually I assume all of you, are familiar with Excel or some equivalent like LibreOffice Calc or similar. And most of your data probably ends up in an Excel document at some point. And so we are going to show how to get something from Excel into R. So we're going to start off by making some data. We're going to make some little toy data, some nonsensical thing about cats, let's say. So we're going to make a data table about cats. Things we need to know about our cats, let's say their name, their weight, and if they like string. So I would say you can go ahead and open up Excel, be working along with me. Most, like Windows definitely, I think Macs as well have a way, oh, not that one. If you take your window and you drag it to the edge, it will oftentimes let you have two things open at once. So you can have like Zoom and Excel open at once, or Zoom and R open at once, like I've done here with R and Excel. Makes it a little cramped for real estate, but oftentimes it's just enough to do what you need. So over here, I'm going to make this data table. I've got names, weights, and like string of cats. So let's see, my cat's name is Spook. And then people I know, they have cats named Mr. and River. Weights, let's put in Spook weighs about 12 pounds. I don't know about the others, so let's say Mr. is like 14 and River is 8. And I know Spook likes string, so I'm going to type in true. And this will come in important later, but type it in all capitals. True. Let's say Mr. does not, and River does. True. So here we have a very, very simple data table. We've got 3 columns, 3 data rows for our cat, Spook, Mr., and River. Now, most of the time when you save stuff like this, you've probably saved it as an Excel document, because that's what most people are used to. For bringing it into R, we're going to save it as a different type of document. Excel documents are actually really complicated underneath the hood. There's a lot of stuff that are saved in those files that have nothing to do with this data we have on here. Stuff about formatting and all sorts of other things that we don't need when we move it into R. While there are ways for R to get this data out of an Excel file, they're a little tricky and a little complicated sometimes. So we're going to go with the simple way that is pretty much guaranteed to work every time. And that's by saving this as a CSV file, a comma separated value file. A CSV file is a very basic data table where it's just plain text. There's no fancy formatting, there's no fancy anything, there's just plain text where commas separate the values in your fields. We won't even have to look at it under the hood. We're just going to save it as that. So take your data table, save as. Save it someplace where you can find it easily. I'm going to save it in my desktop. So here we go to the desktop. I'm going to name this cats. And here's the important part. So as the save of type, where it's asking for Excel, click on that and you have a whole suite of different things you can pick from here. Lots of them. The one you want is just this plain CSV, comma delimited. That's the basic one. There are actually a few others on here, which just makes it kind of confusing. You have this CAV, UTF-F, UTF-8, CSV Macintosh, CSV DOS. Don't get those, just get the plain comma delimited CSV. That's what you want. Click on that, hit save, And now if I go to my desktop, we can see I now have this file cats.csv that got saved here. So I'm going to give everyone a chance to get that far. So make a quick data table, save it as a CSV file to your desktop, and then make sure it actually exists. And when you've done that, type done into the chat. I'll open this back up so people can see. All right, we'll give everyone 30 more seconds, then we've got to move on. I know some people are on phones or otherwise don't have access to the chat, so I'm trying to do my best guess of giving people enough time. All right, so now we have our file cats on the desktop. Now we need to get into R. So I'm going to open up R here. And there's two things we need for this. R needs to know where to look for the file, and it needs to know what the file is. So the first part of where to look, we're going to do by setting our working directory. This basically is telling R, this is where we're going to default everything to, and the default place to look for things in. To do that, up in RStudio, there's a session button, set working directory, and choose directory. So I'm going to just choose my desktop because that's the easiest. If you're doing an actual data analysis, you should probably have its own folder dedicated to just that analysis that you're working on. So I choose my desktop and open. When I do this, RStudio is now doing something underneath the hood for me. You'll notice that down here at the bottom, this text popped up, this set WD and C: users, etc. So this is the command in R that was actually run. And so if you're comfortable just using the text, I could have typed this in instead, and it would work just the same. RStudio is just making it easier for me to do that. So as you start off, probably will be easier, more intuitive to go through the menu and set it. As you get more familiar, it will probably be a good idea to transition to this at some point, especially as you want to keep a record of things in your scripts. So this is how we set the working directory. Now R is basically looking on my desktop for anything I tell it to look for, and it will save things to my desktop by default. So now we're going to load in our cats data. Just can't type today, can I? Load in our cats data. And the function to do this is read.csv. So remember, it's a function, so we have its name, and then we have these two parentheses. Again, with functions, as with variables, case is important. If you capitalize any of these, or if you use an underscore instead of a period, or if you forget the period, it won't work. So we're going to do read.csv, and then it just needs to know the file name. So the file name must be in quotes, and it's just cats.csv in this case. And if I run that, you will see it has loaded in our data table. We have the names, we have the weights, we have this like string. But there is one little problem with this. If you remember, I executed this function here, and so it did something and then it returned the value. So in this case, it did whatever read.csv does, which is it reads a CSV file, and then it returned that information to R, and since we didn't assign it to anything, R just printed it off on the screen and then let it go. So this data actually has not been loaded into R permanently. It showed it to us, and then it disappeared because I didn't save it anywhere. So to save it, we need to assign it to a variable. So I'm going to call this the cats variable. So cats equals read.csv, cats.csv. Now this time it doesn't print it out because instead it returns the information and it gets assigned to that variable cats. If I look at the cats variable, there we have it. And now this is loaded in R, and now I can do things with it. So we are now going to do, let's see here. Oh, sorry, there's one thing we need to do before an exercise. And that's how you access these individual columns. So this is a data table now. It's actually a data frame is the technical name for us, a data frame, which consists of these 3 columns of information. And these columns are kind of like variables inside our variable cats. And we can actually access them by using the $ operator. So if we use the $, we can say cats $name. And if I run that, you see I get just that first column, the name Spook, Mr., and River. I can do the same thing, cats $weight. Have to spell it right. That. Important thing, if you try to access one that doesn't exist, like if I misspell weight, null. That means does not exist. So you have to be careful about this. I have many times made a mistake in my code by misspelling a variable name, and so or misspelling a column name, and so I get null back instead of my actual data, and then it throws the entire analysis off. So this is a thing to be careful about. Just watch your spelling, double check that you're getting out what you actually think you are. So that's how you access these columns within a data frame. Now we're going to do an exercise. So the exercise is going to load in cats, just like we just did. And then I want you to do 2 things. I want you to find the, find the mean weight of the cats, and then add the weights to the owners. Now, this last one sounds a little nonsensical, and that's because it is. This is a teaching moment to show what happens when you try to do things that aren't allowed. So again, go ahead, load in the cats data frame, find the mean weight of them, and then try to add the weights and the owners columns together. And when you have done that, go ahead and type done into the chat. If you give me a moment, if you haven't managed to make a variable, I'm going to try to share one I previously made that you can just download to load in, because I don't want that to be a sticking point for people. If Google ever decides to load. Meanwhile, those of you who do have a copy of it, go ahead and work on it, or if you are working on saving a copy, go ahead and do that. This is only for the people who were not able to make their own. All right, so I have pasted a link into the chat where you can download a copy of the cats data table if you were not able to make it yourself for some reason. Oh, someone's saying the link has a different data set. That's right, because when I did this on Tuesday, we had cat ages instead of weights. That's okay. The numbers may be slightly different, but all the data types are the same.
Hey Jason, what is a owner? You have name, weight, like, string. What is owner?
Owner? Oh, so that's something apparent. I thought that data table was made earlier in the set. So we'll talk about owner later. That's basically adding a new variable to the.
To add a new variable to the table.
Yes.
Oh, okay.
Yeah.
The way to the owner.
All right, I'll give everyone about 20 more seconds. Okay, so reading in the cat's data frame is this same code we used earlier, so I'm just going to copy and paste it. There's no shame in reusing your own code. So this will load it in, which we can check with cats. There's our data. So the mean of the weight is similar to the exercise beginning. We need mean, and we need cats $weight. Or if you downloaded the one from online, you can use the age, whatever. So the mean weight is 11.33. Then we can try to add these things together just like we can other variables. So, oh, sorry, weights to owners. That was a typo. That's what you meant by it. Okay, add the weights to names. So, sorry. If we try to add these two together, we get an error. So, error in whatever, non-numeric argument to binary operator. This error right here, non-numeric argument to binary operator, is frustratingly common. And it is also frustratingly opaque. It's really hard to tell what this means. What it means is you tried to do something that R doesn't know how to do it. And in this case, we tried to add the weights and the names together. And you can make, I mean, this makes intuitive sense. Trying to add spook and 12 doesn't really mean anything. And so R throws this error. But the reason why I had you do this is because oftentimes you're trying to do something that sounds like it should make sense, and you still get this out, which usually means something went wrong. Maybe your variable name is wrong, or you did a typo, or you're not adding the things together that you think, and so you get this problem. And the ultimate problem with this is that weight and name are two different data types, which we're now going to talk about. You can see this isn't just a fact of the fact that it's a column, because we just say cat's weight plus 1, we get a perfectly fine weight. So it's the fact that the weight and the names are two different types of data that we cannot add them together. Specifically, they're two different types of data that we can't convert between each other in a meaningful way, at least not when it comes to addition. So R has 5 data types. And those types are basically the fundamental building blocks of everything in R. They are the tiny little core pieces that everything is all data is made up of. It's kind of like having, like if you had access to 5 different kinds of Legos, but if you had thousands of copies of each of them, you could still build some really impressive things from just those 5 basic building blocks. That's kind of how this is from R. R has these 5 basic data types, but there are ways of combining them in much more complex ways. So these 5 data types are logical, integer, double, complex, and character. Double, for historical reasons, is the way that computer science refers to like decimal numbers. So, and with that, I'm actually going to give you a poll to see if you can figure out what these are. I know we haven't gone over these yet, but this is me trying to implement some things I read recently where trying to answer something before you know the answer actually makes it more likely you will remember the answer when you get it. So just because of the extra struggle involved. So let's go ahead, send out a poll, everyone answer this, try to figure out the data type of these three values. First one is 3.457, second one is true, and the last one is the word green. I'll give you 20 more seconds to throw your vote in. All right, so let's take a look at these results. So data type of 3.457, top vote is integer. I'm afraid that is not correct. If you remember, an integer is a whole number. This is going back to algebra. Integers are 0, 1, 2, -1, -2, but they are whole numbers. They don't have any fractional part. 3.457 is actually a double. Double means a floating point number, means a decimal number. So anything that has a decimal is a double. The name comes from how it was way back in the beginning. It's like double point precision or something. I don't really know the full details of it. That's why it's called that instead of like just like a decimal or something. But that's what it is. It's a double. It is a decimal number. True, and the all capitals here is important as far as R is concerned. Most people got this correct. It is a logical. So true and its counterpart false are part of boolean logic, which you may have heard about if you've read up on some computer science. This is the logic of true and false, where everything can come down to either true or false and just combinations thereof. And so true and false are the logical values. Logical is the simplest of them all because it can only have two values, true or false, nothing else. Lastly, green. And again, this is what most people got correctly. This is a character. So character is basically anything that's alphanumeric, anything that has letters involved, or underscores, or periods, or punctuation, and also numbers, but not just numbers, usually. So this is words and strings and that sort of thing. All right, so we'll go off that. Now we're going to go over the formal definition of each of these, some of which we already covered. So logicals, as said, true or false, which in R is specifically true and false in all capitals. That's how it makes it a special value. You can see here, if I go down to the console and just type true, the value of true is true. Value of false is false. Sometimes you may see these abbreviated as just T and F. That's a shortcut. It will work. I recommend that at first you use the full names so that it's more obvious that you're working with true and false logical values. Integers are whole numbers, like we said. 0, 1, 2, -3, -7, anything that is a whole number. But if it's a fraction like 1 1/3 or -2.5, it is no longer an integer, it is a double. Doubles are decimal numbers. Decimal, there we go, numbers. 2.4, -1.33. Computers don't really do fractions, they only do decimals. So we're not going to worry about fraction numbers, they're just decimals, 7.88, whatever. So if it has a decimal point in any of it, it is a double. Then we have complex. It's imaginary numbers. like 3 plus 2i. You have to remember back to algebra for these. I will say I have never used complex numbers in my analysis. They are probably more important for people who are more into like pure math, but for most practical applications, we don't get into imaginary numbers. We don't use complex numbers, so you don't have to really worry about them from here on out. And then the last things we have are characters, alphanumerics. So letters, punctuation, etc. And there's a reason why I put them in this order. This is the order going from the most restrictive to the least restrictive. Logical values can only be true or false, nothing else. Integer values can be any whole number. Doubles can be any decimal number, which, if you think about it, includes the whole numbers. So like 1.0 is a decimal number, but it also takes the value 1. So Chandler, there's a question in chat. I'm going to get to that in a moment. Complex numbers also include the doubles. So you can turn any decimal number into a complex number easily by just adding 0i or whatever. And then the characters, even though these aren't numbers, like you can't add them together like you can these, you can represent any of these as a character. So the number, it's like the number 32 can be represented by the character 32, the character value 32. So these are different under the hood. This is where these data types are actually important. So the number 32 can be treated like a number. 32 plus 4 is 36. But the character 32 plus 4 gives us that error again, non-numeric argument to binary operator. This is why data types are important, is because they constrain what you are allowed to do. Let's see, let me check my notes here, make sure we're on the right thing. All right, so, and now we get to an important thing called coercion. So these are the data types, but you can move data among these types. You can coerce it to be one type or another based on what it is originally. And R actually does this a lot under the hood. So R changes among data types to try to make things so they fit whatever you're trying to do. So here's adding an integer and a double is like 32 plus 4.1. 32 is an integer, 4.1 is a double. But if I can add them together just fine, because R can look at it and say, okay, this is a double, so this requires the widest permission. It's like I can't make a double into an integer, but I can make an integer into a double. So it turns all of these into doubles, adds them, and I get the result out, which will be a double. Chandler asked in the chat about true and false evaluated 0 and 1. That's how logical values get coerced. So the logical values true and false become 1 and 0 respectively when they're coerced. So you can actually do something kind of strange, like 33 plus true is 34. That's because true gets coerced to the value of 1, and 33 plus false, if I can spell it, false gets coerced to the value of 0. Again, we have a logical and an integer. Integers can't really be coerced into logicals, but logicals can be coerced into integers. And so they'll be added together here. And so what happens is coercion goes from the simplest to the most complex. So if you've got mixed data types, it will coerce from logical to integer to double to complex to character until it hits whichever one is the most complex it has. So if the most complex is an integer, that's where it stops. If the most complex is a double, it stops there. If the most complex is a character, it stops there. Now, most of the time, you don't have to worry about this because it happens under the hood. But there's one specific situation that comes up very frequently that causes problems for people because of this. And that's when you have a typo in your data. So we're going to go back to Excel. Here's our data table with our names, our weights, and our like string. And you can see now we have a character vector, an integer vector, and a logical vector. Now we're going to mess this up by doing something that makes perfect sense to a human being and which R will look at and completely get wrong. Well, it will get it right as far as it's concerned, but it's not what we want. We're going to take this value. We'll say, I don't know what River's weight is, so I'm going to say it's 8 or 9. She's about 8 or 9 pounds. Now I'm going to save this. I'm going to load in that data again. So cats equals read.csv, cats.csv. And if we look at cats, we see it has loaded in apparently correctly. We've got the names, we've got our weights, including this 8 or 9, and we have like string. But now watch what happens. The mean, oops, sorry, up here. We're going to do the mean of cat's weight again. This is the same thing we did in the earlier exercise, and now we get a problem. We get an error. Argument is not numerical or logical, returning NA. This means that we broke R, basically. We tried to ask it to do something it could not do, and that's because this weight here is no longer an integer because we put letters in it. And so now it's something else. And we can actually figure out what that is by using, there, click up there, thank you, the type of function. This lets us know what a variable is. So if I do type of 32, is a double. That's because R defaults to double. So, sorry, that was maybe not the best example. We do type of true, it's a logical. Type of 3 to 7 is an integer. And type of green is a character. So this is how we find things that are the types of. You can do this with variables too. So if we just said like x equals green and do type of x, we will get that x is a character. So there's that. We can now do that, the types of our columns. So we're going to type of cat's name. That's a character. Do type of cat's like string. That's a logical. And type of cat's weight. That's a character. And here's where the problem is. We look at our cats thing again. Weight is supposed to be an integer. It's supposed to be a number value, but it's not. Because we put this or in here, now R looked at that. When it loaded this in, the columns all have to have the same type of data in them. Each column can be different, but within a column it has to be the same. So what R does, it loads an entire column in, and then it looks in that column and says, okay, what is the most complex type of data in this column? I'm going to make everything in that column that data type. So when it looked at this first one, it has a bunch of alphanumerics. Okay, they're all characters. Gonna make them all characters. When it looked in this weight, okay, that's an integer, that's an integer. Oh, this one has letters in it. That's a character. So I'm going to make the entire column a character. You can kind of see this. Let me see if it will do this. R updated recently. Yeah, you can see this in the value. See how cat's $weight, it has these quotes around things. That's another way of telling that these are characters, not numbers. The number will just be a number. It will not have quotes. The quotes means this is not the number 14. These are the characters 1 followed by the character 4, which has whatever ASCII values. This is the character 8 space lowercase o, lowercase r space 9. That's what the quotes mean. It means it's a character. And so this can get us into trouble. Most of the time, people don't add random ors or abouts or something to their columns, although it does happen. I've had to deal with data like that. So it does happen, it's just not super common. The most common thing is that you have a space in there, which by and large you won't notice when you're looking at it because spaces they're white spaces, they're invisible. But R will recognize that that space is there. And so having a space there in your data will turn an entire column into a character instead of into a number. And that can really mess you up. And so this is something you have to be aware of. Okay, someone put in type of cat's name and got an integer instead of a character. I will address that in a moment. That has to do with the version of R you're using because they changed that recently. So let's see here. All right, we have one more thing we need to do before, or two more things we need to do before we get to an exercise. Actually, let's just do one. Chunk it in smaller bets. So the as.something family of functions. This is how you can force things to be coerced in one direction or another. This is a whole set of functions that will change the type of various data. So, for example, if I want to say as.double cats like string, this will take this variable, so our like string, and it will force it to be a double, no matter what its actual thing is. And so you remember, true gets evaluated to 1, false gets evaluated to 0. So true, false, true turns out to 1, 0, 1. Now, these are actually doubles. They look like integers just because there's nothing after the decimal point. Some of you may have 1.0 and 0.0 instead of just 1 and 0. Again, that's a slight variation in R that they changed recently. So depending on what your version of R is, it may be 1.0 or it may just be 1. But under the hood, these are all doubles. You can do as.character. Let's just do numbers 5 through 11. And so this generates the numbers 5 through 11, but then it coerces them to be characters, 5, 6, 7, 8, 9, 10, 11. And so we can actually do this in reverse, as.integer, as.character, 5 to 11, and we will get the numbers back out. You notice they don't have the quotes here. So this is because R can take this string, 7, and convert it into an integer. However, if we try to do that with something that is not a number, if we try to take it with 11a, we get missing. NA. NA means not applicable. This is what happens when you try to coerce something that doesn't work. 11a can be coerced into a character. That's what it already is, actually. So that first part is fine. But then when we try to turn it into an integer, this a causes problem. R has no idea how to turn that into an integer, and so it just makes it missing, NA. And so if you ever see this warning message, NA is introduced by coercion, it means you've tried to change a data type from one type to another where R cannot figure out how to do it, and so it has set some of your data to missing. You can see this. Actually, we're going to do an exercise now. This is a good time to do an exercise. Just a quick one. Force the cat's variable, the cat's weight, to be an integer. And see what happens to the last value. If you haven't adjusted it and messed that up, then it should work fine. If you have messed it up like I did, then you should have a different result out. So go ahead and force the cat's $$ weight to be an integer. And again, type done when you've done this in the chat. I'll give everyone 30 more seconds. Okay, so I'll show you what I did, and then someone I saw in chat had had an interesting thing happen, which again has to do with our version. So we'll talk to that. So I'm going to say cat's weight equals as.integer cat's weight. If we look at cats now, the first two got coerced just fine, 12 and 14. The last one is missing because again, it had the word or in it. Or cannot convert that back into a number, and so it's set to missing. So that's the default. That's the default behavior with current R. Now, someone in chat posted that when they did this, they got that the values were 1, 2, and 3. And this has to do with a default in R that used to be standard and then was changed. So previously, for things like this name value or our incorrect weight where there were characters in it, it wouldn't actually load it in strictly as a character. It would load it in as something called a factor, which is where it, I don't want to get into too much detail here, but essentially it's a way that R keeps track of labels you're going to use a lot. It's used in statistics. It means it's keeping track of it as an integer, but it has a key for saying each value is this word. We're not going to worry about that right now. Don't worry about understanding it. But do be aware that that can cause issues if you if you assume something is a string and it's actually a factor. The way to get around this, loading factors by default, is options strings as factors equals false. So I would highly recommend, if you are using R version 3 point whatever, that you include this at the beginning of your scripts, because that turns off that problematic option. If you're using R 4 point something, this is the default, which makes a lot more sense because it caused a lot more problems in the past than it ever caused solutions. That's all I'm going to talk about factors now. We're going to talk about factors more next week, probably. But for now, we're going to stick with the basic data types of logical, integer, double, and character, because we don't really care about complex values because they don't come up. So there is one last thing to do with coercion. Coercion does the best it can. So we've already seen that if we try to convert a word to a number, we just get missing because there's no rule for that. But there is an important thing that R will do the best it can to convert something, but if you're going from more complex to less complex, you usually lose information in the process. So let's make a new variable. My tongue's getting all tight. Let's make a new variable that contains several double numbers, and we're going to use a new function for this. So let's call it vars. This is the C function. C means combine. This is how you make custom collections of numbers. So custom vectors that contain values. And here in here, we can put anything we want. We can put 14, 27, 91.3, whatever. We'll get to some more options on this in a moment. But the fact is, when we do this, the C function will take whatever we put in here, separated by commas, and then that will make a vector out of that. And so here we have vars, which again, we had 2 integers and a double. Because the double was the most complex, everything got converted to a double: 14.0, 27.0, 91.3. Now we can force these to be different things. We can do as.character. of vars. And we get the characters out. That's fine. We can do as.integer of vars. And now we get the integer numbers. I'm actually going to change this to demonstrate something. So we're going to make it 91.7. So if we do as.integers of this, notice the vars, the last one is 91.7. When you convert it to an integer, you get 91. You do not get 92. Converting a double to an integer does not round. It just cuts it off at the decimal point. It doesn't care anything. You could have 91.99999, and the integer value of that is still 91. So it just cuts it off. It does not round. Importantly, if we convert this to an integer, we have lost information. We no longer have the information that came after the decimal point. So if we convert it back to a double, we do not get the stuff after the decimal point back. We still have 14, 27, and 91. And because they're all 0.0 after the decimal point, it has just taken that off. That's all. That's why it's displaying it like this. But we can check, to make this simple, let's just save it as the variable. We can check it by looking at the type of x. So we're going to save that, look at it. It's still a double. It's just displaying it without the decimal points. This is also true in going to logicals. So logical, we talked about how true and false are 1 and 0. Well, it turns out, as far as R is concerned, 0 is false and every other number is true. So if we take this vars variable, I'm going to actually add something to it. So I'm going to use that C function, and this is a useful thing. You can use it to combine to existing variables. So I'm going to say vars equals C vars, and number 0. So in this case, what it's doing is taking this and then just adding 0 to the end. And I could add more things by just saying, like, let's say 0, 1, 21, and 5.1. So I run that. Now vars has all of these things in it. If I do as.logical of vars, you'll see that everything but 0 evaluates to 0. Evaluates to true. 0 evaluates to false. Everything else is true. And again, this means we have lost information. So if we go back to as.double on this and run it, all we have left is a bunch of 1s and 0s. So we do not get the information back out because in the process of forcing it to be illogical, we have lost the information of what these numbers actually were. So that's the danger in coercion, is that you can lose information in the process. The benefit is that it lets you move things around, and oftentimes, I think this happens under the hood, usually in the case of moving things from less complex to more complex. So I am going to do a quick poll. I didn't have this poll set up, so you're just going to have to type in the chat. What is the data type of this vector? X equals C, true 1.0, 3.1, false 7. So run that. Oh, sorry. This is my fault. You have to have C. It has to be actually calling the function. All right, so what's the data type of this vector? Try to do this without actually typing into R. Just make your best guess based on what we have been talking about, and then type it into chat when you've made that decision. All right, so I've got one answer. You have 5 options. There's logical, integer, double, complex, and character. So far it looks like I've got 2 logicals, an integer, and 3 doubles as the votes. Give everyone about 10 more seconds. Okay, let's find out. Type of X. X is a double. So we can look at Y if we look at these data types. So true is logical, 1.0 and 3.1 are doubles, false is logical, 7 is an integer. So we have 3 different data types here. Remember, R tries to do the best it can, and it will coerce things to the most permissive one possible, the most complex. So logicals are the simplest, integers are more complex than logicals, and doubles are more complex than integers. And so everything gets converted into a double, which means if we actually look at X, you'll see that those true and false values got converted to 1.0 and 0.0 respectively. So that's coercion. R tries to do the best. We can look at this again. If we add in the name Bob and run it. Now, take 5 seconds to think to yourself what data type this will come out as. And then we'll see if you're right. Okay, it is a character. Same reason. Character is the most complex of the data types, and so everything gets coerced to a character. And so if we look at X now, everything is a character. True, which in this case is TRUE, not the logical value true, the character 1, character 3.1, etc. And so this has been coerced to the most permissive one possible. All right, so that is the end of our data types and coercion part. Any questions here? Areas where people are still confused or need some clarification? Okay. All right, lastly, we're going to cover 2 final things. We're going to be looking at data with the function str. This is structure. This is how you look at the structure of data, and it's a very easy way of sort of sanity checking what you've got. You have to learn what the output means, but it can be very useful. So let's look at this. So we've got our X value up here, and we're going to look at the structure of X, strx. So then you get this output, which looks a little opaque at first, but it always follows the same pattern. This first thing is an abbreviation of what type of data it is. So CHR means it's a character vector. This 1 to 6 in brackets means it has 6 elements. And over here is a peek at what those elements are. It's a short vector in this case. It can actually fit them all. If this had like 10,000 elements, we'd only see the first handful. But this is a quick way of looking at your variables and seeing if they actually contain the data you think they do, and if they actually contain the type of data you think they do. So again, if we're going to take off that Bob, run this on X again, and get the structure of X, now it's a numeric. Numeric is basically how R talks about doubles. It's kind of confusing that they have multiple words for the same thing. Most of the time, you're going to get numeric. Every now and then, you'll get an integer. So if we do the structure of 1 to 5, that is actually an integer. But most of the time, you're going to get numeric, which just means double. So decimal numbers. What is useful about structure is that you can use it to look at any variable, including complex variables like our data frames. So if we look at the structure of cats, you'll see that we get now additional data. First off, we see that it is a data frame. So that's the type of complex structure it is. And we will talk a lot more about data frames next time. Don't worry about the details now, just understand they're a way of collecting data together. Tells us some information about it. So the observations of the variables, which are the rows and the columns. But then you'll see we have here a column that's name, which is a character, and it tells you what the values are. Weight, which is an integer, and its values. And then like string, which is a logical, and its values. And so this is a way that you can very easily diagnose if one of your columns is not what it's supposed to be. If weight, actually let's do this, reload that in again. Where, now I'm just going to type it in again. So we're going to do cats equals read.csv cats.csv. And now we do the structure of cats. We get name is a character, weight is also a character. This is our red flag. This says, wait a second, when I typed in weight, weight's supposed to be an integer or maybe a double or a numeric, but I'm getting it's a character, and then you can, in this case, you can see it right then. Oh, there it is, 8 or 9, that's a problem. In most cases, you probably have to dig into the original data and figure out where that character is. But this is one way to diagnose if something has gone wrong in your data, where it is. This is a good sanity check. Is use the str function to verify that data is of the type you think it is. So last thing we're going to be doing is writing data. So we've talked about reading data in. We've talked about all the types of data and how to move it around between the different types. Now writing it back out, which is the other important thing. This is actually not too complex. We read data in with read.csv. We write it out with write.csv. Write.csv needs two things. It needs the data you want to write, the data, specifically the data frame you want to write, and it needs a file you're going to write it to. So we're going to write out cats, and our file is going to be, our file equals catsnew.csv. And so if I hit run, it runs that. So it takes the data in cats, it writes it to catsnew.csv, and if I go to my desktop again, see over here I have catsnew.csv, and I can open that up in Excel, which will take just a few seconds, and we will see that we have the data there. And it's probably not going to be anything too exciting because, frankly, I didn't change it any. But here we have catsnew.csv. It has all our data here. And then you'll notice it has these numbers at the front. These are the row numbers. So this is just row 1, row 2, row 3. That's something that R keeps track of internally. There are ways to make it so that doesn't get printed out, but we're not going to worry about those right now because usually they're harmless. But here we have our data that got written out. Now we can actually verify this works by if we want to change some things. So let's say I want to make a new column for cats called the owner. Cats $owner. Sorry, it needs to be up here. Cats $owner. So just as when we make a new variable by assigning it, R will automatically create it. If there's a column that doesn't exist, but we assign it like this, R will automatically create that column. So let's say our owners are, so it's Jason, Harry, and Christy. So those are the owners of the cats in question. If I run this and I look at cats again, you see we now have a new column which has the owners. And if we look at the structure of cats, we have the owner here is a character vector with these things in it. And I'm just going to run this same line again to write. Oh, permission denied because I have cats new open in different window. There we go. So close the window, run that to write it out. And now if I open up the file, you'll see the changes we made to it. So now we have our data and we have the new column here. So that's how you write data back out using the write.csv. You need the data, you need the file name to write it to, and it will put it out there for you so that you can then open up again Excel if you need it for some reason, or to send it to a colleague or anything like that. So, final exercise. Add a column to cats for the age. And the ages we're going to say are 7, 9, and 14, respectively. Verify that it worked. So confirm it worked. So make sure one way or another that that column got added. Write the updated data frame to a file and open it. So this is your exercise. Add a column to cats with the ages. Make sure it worked through any one of the ways we've talked about, and then write the new data frame to a file and then open it to make sure that it did actually write the right thing. So go ahead and do that. I'll give you all a few minutes to run that, and then when you are done, go ahead and type done into the chat. All right, I'll give everyone about 30 more seconds, and then we need to wrap up. Okay. So the way we go about doing this, we have cat's age, make our new variable using the C function with 7, 9, and 14. Run that. One way of checking is just typing out cats, or we can do structure of cats. Also works. And both ways we can see we have this age column here. Then we write it out. So write.csv. We're going to write our cats data, and our file is cats. I'll call this exercise.csv. Run that, check on my desktop. Here it is, and it can be opened in Excel. And so here we've got the life cycle of data. We've got reading it in, we've got manipulating it, we've got writing it back out, which is, in a nutshell, most of what you're going to be doing in data analysis. That in-between part, the doing something to it, can get really, really complicated. But ultimately, most analyses are some variation of what we've just done, of reading in, manipulating, writing out. All right, here we go. So before we close up, I have one final just shortcut to show you, or not shortcut, but quality of life thing. So I don't know if you've been able to see it because my chat window's been blocking it, but if you look in the upper right-hand corner of RStudio, you have this environment tab. And if you look at what's here, you realize that some of this looks familiar. This is basically the output of that str command. So if we do str of roots, you'll see that the values that come out here, or this whole thing here, is the same that's up here. This is basically a preview of the variables you have in your environment right now that you've loaded into R, and effectively what would happen if you were to run the structure command on them. So we can see that roots is numeric. It has 9 values, and these are what the first few of them are. Temp1 is an integer with 9 values. This is what they are. Up here we have cats, which is 3 observations of 5 variables. So it's 3 rows, 5 columns. And if I click this little arrow over here, you can get the details, again, from running structure on it. So this is another way that you can double check things. Many people like to use this environment just to do a quick check on something if they don't want to have to type it in over there. It's a good way of keeping track of things. You don't have to use it. Some people just ignore it entirely. But if you find it helpful, it's there. So that is that for today. Are there any, well, okay. What questions do people have of today's stuff? I know there was a lot of things. I know it can be complex. I know some of you are probably struggling with the stuff we're going over. That's okay. In fact, I was reading earlier this week about learning styles, and the mere act of struggling to learn something makes it more likely that you will remember it later. So even though it's hard, it actually, long-term, it serves a benefit. So what questions do people have over what we've covered today?
So Jason, I have the problem of the factor, the version read it as a factor instead of the actual, nature of the data. So I run that option stringsAsFactor equals false. And then when I ask for the structure of the table, it still tells me that those are factors. Okay. I can send you my screen.
Here, try this. So you ran the option, try loading the data back in with read.csv and then look at it. See if that changes.
Okay, gotcha.
Yeah, I did the same thing, Julia. I went through what you went through, but then I ran the option and then I reloaded the data set and added everything in, and then I did the structure.
Yeah, because by running that option, it doesn't turn off, it doesn't change the data you already have.
Yes, that makes sense. So. That's right. Okay, thank you.
No problem. Other questions?
This is maybe a silly question, but if you accidentally typed in a command wrong and you keep getting those little plus signs over and over again every time you press enter, how do you stop that from happening?
Oh, okay, yes, that's actually a very good question. So let's say x equals c. And so if I type that in, you'll see down here at the bottom I have this plus sign. That's the sign that R says, you're not done yet. I'm still waiting for something else. And it's not always clear what that something else is. In this case, this is a very simple command. And so you can see I have an open parentheses, but I do not have a closed parentheses. So I close it, okay, R's happy, it runs the command. Sometimes with more complex things, it can be a while. And you'll notice if I down here and I'm just hitting enter, like it never goes away because it's still waiting for something. So if you don't know what,
if I put the parentheses in, it works, but I don't know what I did a while ago. I put in a parentheses and everything, and it just skipped.
Yes, the way to get out of that is escape. If you hit the escape button, come on, R, that will cancel out what you're doing. Sometimes you have to hit it more than once.
Okay, that's great tip.
That's also a good tip. If you start running something that's taking forever, you can hit escape a few times, and that will cause R to cancel what you're doing and get back out. That's useful if you run something that you think will be fast and it turns out not to be, and you need to do a few other things. So escape is basically the cancel button for R. Other questions? Okay, Just a sec. I'm going to stop the recording.